Let's get started while people are still joining.
Okay, good. Let's get started. Hello, everyone. Good morning, good afternoon, and good evening in different places in the world. My name is Xiaodong Zhang, and coming from Ohio State. This award presentation session will be hosted by myself and Professor Xiaobo Zhou, University of Colorado, Colorado Springs. He's the current TCDP chair. So before we present the awards, I would like to take this opportunity to thank the leaderships of this year's ICDCS conference for their efforts on many dedicated arrangements of the conference and to select the high quality papers for us to get together in this leading forum of distributed computing. So specifically, I would like to thank General Chair, Professor Sung-Ching Chen from George Mason University. George Mason is very close to Washington, DC, and we plan to have this conference in DC, but now we're online. And program co-chairs, Professor Abhishek Chandra from University of Minnesota and Professor Delma Del Silva from Texas A&M University. Of course, and many other people who are working very hard for the conference. We truly thank you for all your hard working and contribution to ICDCS. If this is a physical conference, we will have a round of applause. We truly thank you for your great efforts. Thank you. The research areas in IEEE Computer Society are divided by the technical committees. So the distributed computing research belongs to the Technical Committee on Distributed Processing. And this is the TCDP. And the ICDCS conference is the major conference sponsored by TCDP. And so let me first introduce the TCDP Award Committee. So under TCDP, we have Award Committee. So the Award Committee consists of the following members: Ken Berman, Cornell University; Jianong Cao, Hong Kong Poly University; Chita Das, Penn State; Nancy Lynch, MIT; Michael Renell, University of Rennes, France; Jie Wu, Temple University; myself from Ohio State; and Xiaobo Zhou, who is also a member of the award selection committee as the TCDP chair. So let me first introduce Professor Xiaobo Zhou, who is the current TCDP chair, to present the service award. Xiaobo.
Hello, everyone. It's very nice meeting all of you. And thank you very much for helping us, for this award session. And on behalf of the IEEE Technical Committee on Distributed Processing, it's my honor to present 2021 Outstanding Service Award to Professor Chen Zhongxu for his long-term service in distributed system and chair TCDP for 2 terms. And let me introduce Professor Xu and highlight his achievements. Professor Chen Zhongxu currently is the Dean of Faculty in Science and Technology in University of Macau. He also holds a chair professor in Computer and Information Science. He chaired TCDP for 4 years during 2015-2019. Importantly, he restarted the Outstanding Technical Award and created Outstanding Service Award. He also frequently served ICDCS Program Committee and served the PC member many times. He chaired the ICDCS 2021 Best Paper Selection Best Paper Selection Committee. He also served as the associate editor for many flagship journals in the area of distributed system, including IEEE Transaction on Parallel Distributed System, IEEE Transaction on Computers, Journal of Parallel and Distributed Computing, and he also served as general chair and program chair for many conferences in the area of distributed processing. He, including the general chair of the IEEE ACM-CC Group 2015. Due to his contributions to resource management in parallel and distributed systems, he was named as 2016 IEEE Fellow. Congratulations, Professor Chen Dongxi, and please give a short remark.
Okay, so thanks, Xiaobo. And so it's my great pleasure and also great honor. My service and to the Tcdp community is recognized by the World Selection Committee. I appreciate it very much. So by taking this opportunity, I would like to thank a number of persons who advised me or guided me through the years in professional services. And so first of all, I'd like to thank Professor Michael Liu, and who is the former steering committee chair of ICDCS, and who taught me to be goal-oriented in community services, and also from his own passion over the years. And also, I'd like to thank Professor Xiaodong Zhang, and so my longtime friend, and also the mentor in research, as well as he is also the current steering committee chair of ICDCS. So he set a role model of dedication. So I appreciate that. And so for the first time, we also work together to streamline the way of cooperation between ICDCS and Tcdp. So this is should be the first time. So and also I'd like to thank the former Tcdp chairs, Professor Jie Wu of Temple University and Professor Jiandong Cao of Hong Kong Poly U. So they laid down good foundation for me to reinstall the technical achievement award to recognize the person's contributions of individuals who deserve. And so once again, so thank you all for the award, and for sure it provides me good incentive for me to service more and better to the community in the future. Thank you.
Congratulations.
Thank you.
So another annual award selected by our committee is Outstanding Technical Achievement Award. So the purpose of the award and the qualification of the awardees are defined in the slides. Let me go over this. To recognize scholars whose technical accomplishments and contributions significantly to the advancement of distributed computing system field in the following three ways. First, it should be in one of the following three ways. First, impact on significant achievement impact on significant and foundational advancement of the field, which is the distributed computing system field. Second, impact beyond the basic research to industry practice. And the third one is impact beyond the field to the society. So I'm very pleased to present the 2021 Outstanding Technical Achievement Award to Dr. Dalia Maki. So I'd like to highlight, let me also make the citation for her practical and foundational contributions to distributed computing systems. Let me also make some achievement highlights to Dr. Dalia Maki. Dalia is currently CTO of the DM Association, leading the technical effort on blockchain technology. He is co-inventor of Hot Stuff, the consensus algorithm in the DM blockchain core. He is a co-founder and technical lead of VMware blockchain project. He is a co-inventor of flexible Paxos that is being used in Facebook and others. And he's elected as ACM Fellow in 2011 for contributions to fault-tolerant distributed computing. Congratulations, Dalia. I'd like to ask you to make a short remark.
Thank you very much, Anton. And thank you, everyone. All I can say is I'm very honored to receive this distinction. I'm humbled when I see the list of awardees that were granted this award before me. I'm honored to see my name next to such people, and also the award committee. To have my name appear on any page or any slide next to all of you. So I'm very honored and thankful to all of you for this distinction. I also want to say, this is a very practice, merging with foundation forum, conference, and this particular award. And when I received the notification, the email notification about this award, I was very, very busy in hectic times around production, as happens. I didn't even respond. It was pushed aside. It was not an emergency. So I apologize to the committee for keeping you in suspense for probably a couple of weeks before responding. But that's what happens sometimes when you're working on tech. In the end, I did respond. We have connected, and I got this nice black plaque behind me with this award, which I'm very thankful for. So all good. Thank you.
Okay, thank you. Congratulations again. Just a few weeks ago, I received a short video from Professor Ken Berman of Cornell University. So before your keynote, I'd like to play that video, and Ken also wants make some comments and introduce your keynote. Let me get back to another short video.
Hi, I'm Ken Berman, and it is my great pleasure to welcome and introduce Dalia Malki as this year's winner of the Distinguished Research Award for ICBCS based on past work done, and also as today's keynote speaker. Let me tell you a little bit about Dalia. I've known her for many years. In fact, when she was a graduate student, she spent some summers in my research lab at Cornell University, and we collaborated on a number of distributed systems papers. She, in that period, was extremely prominent and, in fact, became a faculty member at Hebrew University, where she did her PhD also, and was very visible in both the theory and practical side of distributed systems. She did some work with Mike Ryder that led to the invention of a technique called Byzantine quorums that was published, I believe, in ICBCS at the time. Just beautiful work on showing that quorums can be used in two-dimensional grid setups in order to gain availability and also flexibility of a useful type, especially when a system had variable latencies. She went on to eventually move to Microsoft in Silicon Valley, and there she worked on a system called Kofu, a logging system which has been extremely influential. She was one of the lead developers, and after Microsoft disbanded, she became a founding member and lead researcher at VMware, which at the time didn't have a research effort. Today, they have a substantial research group, and we can point to Dalia as the builder of that. So since then, she's moved to Facebook, and in fact, to Facebook's spinoff, the company called Novi Financial, where she is the lead researcher on creating their new DM currency. So with her background in distributed systems and Byzantine agreement and quorum solutions, you can see how it's all coming together to give us perhaps a real alternative to traditional currency. So with that, let me welcome Dalia for her actual talk and say that I'm so sorry that I can't be there in person, Dalia, to give you your award and to attend the talk. In fact, I'm in a farmhouse somewhere in France right this moment, but I will try to join in and ask some questions after you're talking. If I can't join in, at least I'll be able to see the recording. So Dalia, congratulations again, and the floor is yours.
So
Thank you again, Shodong. Should I
please.
go on right away? Just a time check. Should I wrap up around the hour or before that for Q&A? What's the plan?
Sung-Ching, is this the last session?
Take your time.
Yeah, just
right.
take your time. This is the last session of the day.
All right, so here's what I'll do. I'll wrap up at the hour, and anybody who wants to stay for Q&A is welcome to. So let me share screen, see if that works. Everybody can see my screen still?
Yeah.
Super. And I can still see you, so all good. Thanks again for the award. Thanks again for inviting me to speak. I spent the last 2 decades being an industrial researcher in the Silicon Valley, involved in building various advanced tech systems. This was my choice. I started my career as an academic professor, but I find that I really liked being involved in the execution and the impact of innovative techniques. I ended up leaving my academic position for Silicon Valley jobs, first spending a decade at Microsoft Research, later building a new research lab at VMware, and most recently leading innovation pipeline for modern fintech arena systems. I was fortunate enough to be involved in several systems that reached production and impact and became part of successful products. And I wanted to share with this audience the stories of 4 such systems. I may have to skip one because of time. And just to tell stories behind the scenes of how these systems transpired and what drove them to impact. All of these stories are in the distributed computing arena, but even more specifically, they really all focus around this very basic and foundational notion of state machine replication. But the lessons and the insights behind these stories, I hope would be interesting for you, no matter what discipline you're in. So I labeled these stories. The research product flywheel, too much abstraction, too little abstraction, the value of unlearning, and developer first. Like I said, I may have to rush or skip one of them. Let me start with some high-level insights on what I would call the research flywheel. I'm going to start with a quote from one of the researchers who impacted my personal career the most. This is Leslie Lampert. He used to tell the researchers at Microsoft Research that if we want to do impactful research, what we should do is go to the engineers, find out what problems they're working on, and try to solve their problem. And to quote him, he said, if I just work by myself and come up with problems, I'd come up with some small number of things. But if I go out into the world where people are working on real computer systems, there are a million problems out there. When this is Leslie, going back, look back at most of the things I worked on, like Byzantine generals and Paxos, they came from real world problems. So this has been my North Star and the North Star for a lot of us researchers coming out of the Silicon Valley Microsoft Research Lab. And indeed, if I want to share insights, my 2 cents experience from this flywheel effect of research working embedded inside industrial production systems, I would say there are 2 main takeaways. One, tech transfer is a 2-way stream. And in fact, the very term tech transfer seems to indicate that researchers take a great, glorious, brilliant idea and transfer it to tech. But actually, often it's the other way around. Often engineers have tremendous insight into the systems that they're building, and they come up with creative and original and innovative solutions. And then researchers can come and provide structured foundational understanding, and then feedback into enhancements, optimizations, improvements of these systems, and create this flywheel of feedback loop that feeds better research as well as better production. But it's by no way a one-way street. And the second takeaway is that it usually takes people. So tech transfer is less about the tech, it's more about the people who are involved in the tech. And usually I found that it takes two people on either side. So research to prosper and succeed needs to work in a somewhat siloed way. The only way we knew how to do cutting edge first-class research is to put researchers in a somewhat siloed manner, and to really let them be less structured, less time-oriented, and less goal and deadline-driven than production. And production, on the other hand, is optimized for caution, for high assurance, for making sure that systems in production don't fail. And this is how people are incentivized and promoted in production. And I don't say this in a critical way, I say this in the most positive way. This is what they're paid to do, and that's a good thing. And to really bridge across these two worlds takes typically two people: a champion on the research side who's willing to put aside research and to look at all the brilliant, extremely important technical achievements that research come up with, and ask what really solves a problem that will get us to a better product. And on the other hand, needs a champion on the engineering side who's willing to listen and appreciate working with researchers. That's the way it works in my experience. And when it succeeds, it's a remarkable flywheel effect. It can really loop back and create impact. So I will proceed to tell the stories of a few tech transfers that I was involved in. To a large extent, the attraction of these stories is their success or their impact. But I actually want to focus on the foundational impact that working on these systems brought back into the distributed computing arena. So I'll start with, as I said, all these stories revolve around this very simple and succinct notion of state machine replication, which I believe doesn't need introduction to this audience, but just to level set and get everybody on the same page, let me spend 1 minute and say, what is state machine replication? And the nice thing about it is that you can really define it in 2 sentences. It's a very powerful notion. The idea is that you could construct a reliable service on a group of machines or nodes, each of which might fail on its own, but you trust the group as a whole to remain intact and to keep the service uninterrupted. And the way state machine replication works is by replicating the service state and its output by constructing each server as a deterministic state machine, and then guaranteeing that all the servers process an identical sequence of state machine commands, and thereby they're all in the same state. That's all there is to it. It's a very simple but extremely powerful notion that essentially underlies all reliable systems today. So here enters the story that I labeled too much abstraction, and the story of vertical Paxos, a new algorithmic foundation that emerged from that high abstraction. So one of the many of the very early and most insightful abstractions in the field of reliability is that you can reduce state machine replication to the problem of solving agreement, consensus, only once. If you can solve it once, then you can use it again and again to form agreement on any arbitrary decision value, and then you can form a sequence of state machine commands that you form agreement on. So this elegant reduction underlies the key approach that exists for decades and many of the early and foundational solutions. And again, there are probably thousands of papers by now that focus on the key core difficulty and solutions to it, and that's the consensus problem. I arrived at Microsoft Research as a younger, I'm still young, but a younger researcher in 2004, where Leslie Lamport was one of the prominent researchers, and of course, a pioneer and a founder of this approach. And I came up to him and posited that this insight and this very nice, elegant mathematical reduction of taking state machine replication into a single consensus problem. While it is correct, it does not reflect the way engineered systems are really built, and it's oversimplified. Okay, that did not go very well. Leslie was not happy to hear that. So it took about 4 years of very vocal discussions. At some point, we added to these dialogues another young researcher, Li Dongzhao. And 4 years later, in 2008, we published a new state machine replication foundation, which we called Vertical Paxos. Before I mention a few words about what Vertical Paxos addresses, I want to say that special cases of Vertical Paxos actually popped in other works. Yahoo Lab researchers, Reed and Junquera, observed that state machine replication works better with prefix-based agreement instead of individual agreement decisions, while they were developing the system called Zookeeper. And they had a paper about it published later in 2010 that was probably worked in parallel to us. Stanford researchers, Ongara and Osterhout, we heard Osterhout's keynote yesterday, also formed this notion that prefix-based SMR works better in an engineering setting. And they developed Raft, which is essentially the same observation, and published their paper in 2014, so 6 years later. The same observation actually appears already in the early foundational works by Oki and Liskov, who developed view-stamped replication back in 1988 at MIT. But view-stamped replication did not have an algorithmic foundation to it. So Vertical Paxos in 2008 essentially gives algorithmic foundation which generalizes and encompasses all of these. Since it's a publication, numerous systems were built using Vertical Paxos. Some existing ones simply understood and had algorithmic foundations to reason about it, and also to with more confidence produce enhancements and variations. And this is the flywheel effect, where better foundations lead to better engineering and vice versa. So let me quickly talk about what is Vertical Paxos. So when you look at this abstraction of reducing state machine replication to a sequence of single consensus decisions, there are a number of immediate problems with it. One is there could be holes. If agreement is formed on each decision independently, then we may have a decision for, in this picture, number 7 and 8 in the sequence before we reached agreement on number 3 and 6. Now, this doesn't actually happen in most engineering systems in practice, but the algorithmic foundations allow that. And engineering had a really hard time faced with this abstraction. What do you do with the actual commands? You cannot process command number 4 and 5 before 3 is agreed on. And what do? Do you queue them? And you have to solve agreement on the queuing problem. And this becomes really complex. The second problem is that the most consensus protocols are leader-based, and the leader is replaced when one leader is faulty. The problem is that when a new leader emerges and there are holes in the sequence that the previous leader left, then the new leader will have to fill in those blanks. And the previous leader might have intended to execute a sequence of command contiguously. You cannot just go back and fill holes with something else. So that creates a lot of confusion in practice. It's even more exacerbated when the holes that are being filled, whether by the same leader or a new leader, actually contain control commands that change the state of the system itself. Then, the control command was meant to take effect in the command that followed. But then if you didn't reach agreement on them and continued processing new commands, then the new leader doesn't know what to do. And these anomalous situations, I could go on, and I won't, but you could create situations where 2 new leaders are replaced one after another, and one of them left a command that is a whole, the second leader saw it as a whole, so ignored the control command. But then a third leader actually sees that command and commits it. And you could create really, really strange situations that way. The fourth and last problem is that the very notion of state machine replication by a sequence of consensus decisions conflates two notions: the notion of durability with high availability. So actually, when you think about these systems need to replicate service state so that it doesn't get lost and that it's durable. And to tolerate F failures, you only need F+1 replicas for durabilities. But as we know, F+1 replicas are not sufficient for control commands. If there are failures, in order to continue operation against partitions, then you actually need 2F+1. But there's no reason for the control commands that manage the system configuration to have the same deployment and the same fault tolerance as the commands that are processing, and keeping the state of the service durable. So really what you have is a conflation where a sequence of commands have normal commands that need only a primary and some backups. In the most common case, just primary and one backup, just two replicas, just two copies. And then whenever something goes wrong, whenever you need to change the configuration and do a view change, then a control command kicks in, and it needs 2F+1 to solve consensus. And again, when you look at production system, nobody deploys expensive servers with storage capacity to maintain an entire history of commands and their state more than is needed. So if you need F durability, then you deploy F+1 copies. You do not deploy 2F+1 database servers or disk machines to store copies that are not necessary. So vertical Paxos enters with a slightly different algorithmic foundation than the typical one that Paxos and the other state machine replication foundations provide. And it's just something pretty simple. You start the system with a contiguous sequence of commands that are made durable by persisting them to a primary and as many backups as needed. For this, you deploy F+1, where F is your resilience threshold. Then when something goes wrong, when there is a failure, then you can seal the prefix of commands to the point where they've reached, and start a new configuration. And that configuration will be concatenated with the previous one, so that you stagger these prefixes one after another. Each time you seal a prefix, you start a new world at the tail of the previous one. And each one of these views or configurations forms a contiguous prefix of commands. And in order to facilitate this sealing and also to manage the configuration and decide what will be the next contiguous sequence, there's a different system called the configuration management system that makes those decisions on view changes. And that system in itself is a state machine replication system, and it employs something like Paxos. It does need higher, to form consensus decisions, so it needs higher number of copies. But those servers are lightweight. They don't maintain state. They don't maintain the history of commands. They only kick in to manage configuration. And this is really the way engineering systems are built. Almost all engineering systems today, since vertical Paxos was published, look like this. So the takeaway from the vertical Paxos story is, the industry was grappling with essentially an over abstraction, something that works correctly mathematically. It's a beautiful and elegant reduction, but it's an oversimplification. And this created a gap between what the engineers were doing and the foundations. What we saw is that engineered systems either resorted to using Paxos or other algorithms by passing one command at a time, or they were actually implementing essentially vertical Paxos without having the right abstractions and algorithmic foundations to think about them. And since publishing vertical Paxos, engineers are using it to reason and to have confidence about their own systems. So a beautiful foundation, really one of the most important and favorite problems of mine in the field, the Byzantine generals problem, needed more work to actually bring the flywheel effect. So second story is the story of too little abstraction. So this story is the story of Kofu. I'm going to rush a little bit through it. The story of Core4db started with an opportunity to participate in Microsoft's SQL team migrations to cloud systems, and specifically to SQL Azure, Microsoft's cloud databases service. So in this story, in 2012, Phil Bernstein approached me at Microsoft Research with the following observation. He said, databases for decades were optimized for small memories, large disks, and how to optimize index structures that are stored on disks. But actually, in the past decade then, real memories have grown so cheap and so large that the index of most database systems can be held in memory. Not the data blobs, but the index can be stored completely in memory. Or even if not, then all the hot items, they can be indexed directly in memory. So this leads to a different design of database systems where the index is in memory. It doesn't need to optimize for disk access. Transactional systems are built with an index data structure that is optimized for operating this way. And Phil's team at the time worked on a system called Hider, which later became part of SQL Azure. And the key enabler they needed is only to persist with very high throughput and reliability, the commit log of commands that are then reified and materialized in an in-memory index. So what he needed was a reliable, high throughput distributed log. So I saw an opportunity and I said, great, this is something we should know how to do in the distributed computing field. I managed to convince two colleagues at Microsoft Research back then, Mahesh Balakrishnan and Vijay Prabhakaran, and later a summer intern, and later somebody who became a colleague and researcher of mine, Michael Wade, joined the project. And I basically told all of them, let's work 3 to 6 months on this project. This will not be research, this will not produce any papers, but it's an opportunity to drive real impact and put into practice our expertise. So jointly, we embarked on Core4db, a distributed log designed to support the databaseless DBs. And we designed Kofu to scale out by striping it across a cluster. So what you see in the graphics here are the stripes color-coded. Each one of them is its own durability world built of F+1 replicas. And what we needed is a very fast way to remove contention from each one of those stripes, because each one of them could support consensus, but the most efficient way to make sure that there's only that every attempt to append to the log succeeds and there's no contention is to schedule the append request to the log such that there's no contention to begin with. So it would, to put differently, it would really be wasteful for many processes to try to append to the same log position when it's striped all over the cluster, and only one of them to succeed. We wanted only one to try and append to the same position in the usual case. So to avoid any fail requests, we set a network scheduler, which we called a sequencer, that hands out these tickets to append to the log at different positions. And then there's no contention. Everybody proceeds and appends. There was also a lot of innovation and cool stuff happening on top of the log in building transactional processing on top of a shared log. But what I really want to underscore is the foundational insight that we took from building this striped log, which is really the ground truth of the Core4db system and the foundation. So when you look at this design is nothing more than a state machine replication, but really the devil here is in the details. The sequencer is obviously a consistency and atomicity bottleneck. The sequencer is the one that hands out the tickets to every append request. So it looks like we only shifted the bottleneck to a centralized place. However, the sequencer is a memory counter. It can be extremely fast. It doesn't need to persist anything, and it doesn't do any IO or process any commands. So it's really not part of the state machine replication in any serious way. So even though it's a centralized component in the system, it is extremely fast. So it took a little bit more than 3 months, but by the end of 2013, about 2 years later, we had a Kofu log that worked at close to 1 million transactions per second, striped across a cluster, and can stream read requests at essentially scale-free manner, whatever the bisection bandwidth of the cluster network could allow. So I want to continue the story behind Core4db just a little bit longer, because what happened in 2014, we were still working on the Core4db log and supporting a Microsoft system when, bang, Microsoft shut down the Silicon Valley Research Lab. This was a very sad event in the research community, but Mahesh and I and several others moved on and became the founding members of VMware Research Group, this new research lab. And here enters the story of too little obstruction. So VMware's product line is to manage computing workloads. And what we learned is that cluster management builds a spaghetti of systems. If you looked at Lambda architectures on micro services in any cloud, there are spaghetti of systems that start with an event stream of some sort, logs it, and then there are sometimes a dozen or more database systems that take events out of the log and reformat it and put it in a database so that they can analyze it and manipulate it. So this was clearly the case of under obstruction. And we came with the Core4db aha insight and said, well, what if there was a high throughput log that can serve as the ground truth, source of truth for all of these systems, and everything else would be supported by an in-memory transactional library that is easy to program with. And indeed at VMware, we rebuilt Core4db to serve distributed control planes for large clusters. And 7 years after we started our 3-month digression from research, the little diversion we took in 2012, 7 years later in 2019, we shipped, sorry, that should be 2018, we shipped VMware's NSXT management cluster, a management plane which is powered by Core4db. And just to mention, NSXT as a product sells for over $1 billion annually. All of the data, all of the state which is processed in the NSXT management cluster is handled by the Core4db data platform. So Core4db takeaways. Well, aside from don't ever listen to Dalia when she says drop your research for 3 months and do something with me, I think that by now log-based systems are quite prevalent in Kafka-based products like Confluent and in many, many other systems. I found it really worthwhile to work on that system. We did publish a lot of papers out of it. We did find a lot of opportunities to innovate. And at VMware, Core4db serves, as I said, as the data platform underlying NSXT. And at Facebook, in the last 3 years, a system called Delos was built by Mahesh and a team, and drives a control plane for dynamic cluster storage backend systems. Moving on, story number 4 is the story of flexible Paxos. And this story dovetails Core4db. While working on Core4db, we were repeatedly asked, well, how exactly does the role of the Core4db sequencer compares to a Paxos leader? Clearly it is not, but do we have the algorithmic foundations to reason about it? So in the summer of 2016, I had a summer intern named Heidi Howard. And I asked her to look at this question. And 2 or 3 weeks later, she approached me with a very, very surprising observation about Paxos. She said, well, each of the phases of Paxos may actually use non-intersecting quorums. Only quorums from different phases are required to intersect. Only across view changes are they required to intersect. Majority quorums are not necessary, as intersection is required only when you change the view. This was really somewhat shocking because everybody in the field of distributed computing, everybody working on Paxos and consensus knows that basic property you would require from quorums is intersection. So what gives? So recall that in vertical Paxos, a view has a fixed configuration and a fixed leader, and is really only used for durability. Now, for durability, the leader can choose any backup or backups, and can persist commands to any subset so long as they have f+1 copies. Remember, this was one of the insights of vertical Paxos. Well, in particular, a system could consist of more than f+1 or 2f+1 or any number of storage servers. And this was indeed the insight from Core4db. If you want to stripe for throughput your reliability system, you can do that over many subsets of f+1, not one, not two, and non-intersecting ones. In order to change the view, it needs to seal, and then the new view must extend the existing one. Oops, sorry, didn't mean to jump. So this requires intersecting with the previous view, but only when you change the view. So what Heidi observed is that within a view, the leader could have multiple durability sets that do not necessarily need to intersect. And only across views, they need to intersect. So this insight has a number of interesting aspects to it. First of all, this was discovered after 4 decades of research and development and tweaking and studying to death Paxos-based systems. And here comes an intern with an insight that nobody else saw. By removing the intersection requirement, flexible Paxos really enables a new breed of scale-out systems like Core4db and others. One of the most interesting insights into what happened after Flexible Paxos was published is actually that several teams, to take one example, YouTube contacted us and said, yes, we are building systems that way. We realized that the foundations were incorrect. We don't need quorum intersection. But when we approached experts in the field, they dismissed us. They said, you're wrong. Quorums in replication systems and in state machine replication have to intersect. So this was really interesting. And again, the flywheel of researchers listening to engineering insights and the way they really solve problems, leading to better foundations. Since the publication, Facebook also took Flexible Paxos and used it to build a scale-out messaging bus called Log Device, as well as other systems. And I'm also going to take the John Osterhout measure of impact from yesterday's keynote and mention that Werner Vogels, the CTO of Amazon, tweeted not only about Raft, but also earlier about Flexible Paxos. So the takeaway from this story of tech transfer is that sometimes the most useful piece of learning is actually unlearning it. And this is a quote from Antisthenes. I want to finish with a last short story. I only have 6 minutes, so I really breeze through it. And this is the story of the hot stuff and the core state machine replication engine that we use in DM. So renewed interest in blockchain world on scaling and robustifying replication system really sparked and unlocked a lot of new techniques and interest in scaling and in trustless, in building systems, building trust over trustless backbones. And in 2016, when we founded VMware's blockchain project and we looked at the state, we found that the existing foundations for Byzantine fault tolerance, this is now state machine replication, which is meant for a failure model where nodes are not trusted, they may be compromised. Those foundations were lacking in several ways. First of all of them, when they rotated a leader, required a quadratic number of messages. Now, why would we care about a theoretical measure? Well, when the Byzantine generals problem was formulated, there were 4 nodes in the system connected by a fast local network. But blockchain systems are designed to operate over a wide interconnect with orders of hundreds of nodes, sometimes more. So this means that to rotate a leader would require tens of thousands of messages just for a single decree. And these messages are sent over long-haul communication links. There are also some attempts to linearize at least some cases. The prevailing one was called Ziziva. And so we looked at it and said, oh, okay, great. So for most cases, there is a linear solution. Unfortunately, Ziziva was broken, and we've indicated how. So if we paused here and we're only interested in research, we would probably have a table like this one that shows everything that preceded us, several complexity measures, fault tolerance threshold, number of messages to consensus decisions, number of messages to rotate the leader, and so forth and so on. Would show, a nice paper that improves these theoretical measures. And indeed, hot stuff is the first Byzantine fault tolerant consensus algorithm that has linear leader attention. However, what I want to highlight is that beyond algorithmic complexity, we were really concerned about building robust, high assurance software that could last, thousands of years. Blockchains can be forever. And what was really lacking is developer friendliness. And to quote James Mickens, whose picture I borrowed on this slide, he says when he looked at BFT consensus, it was the saddest moment of his life because it was so complex that a non-expert could not understand this. So really, in Hot Stuff, what we did was we looked at the tremendous innovation that was occurring in the blockchain arena outside academic circles. And we looked at Nakamoto consensus, which was a remarkably simple algorithm designed for different settings, and borrowed insight and simplicity from that world to produce a very simple algorithm that has the look and feel of Nakamoto consensus, has the linear complexity reader rotation that we wanted, but it doesn't have the drawbacks of public blockchains, like consuming tremendous energy and not having clear guarantees of finality. I did want to flash, very quickly slides that show just how simple the Hot Stuff algorithm that was adopted by DM and branded DMBFT as the production system is. Let me see if I can do it in 2 minutes. In Hot Stuff, blocks are chained, just like any other blockchain, by extending the tail of the current chain. Unlike Bitcoin or Ethereum driven by Nakamoto consensus, the way blocks are chained is not by solving a very difficult computational problem, but by having a permission set of nodes, we call them validators, that are voting on the block. When you collect 2f+1 votes, we form what's called a quorum certificate. You certify the block, and then you can continue. And what 2f+1 votes guarantee is that only one block can be certified at any round. Now, what can happen is that either a block gets certified and the chain continues growing, or the participants, the validators, time out and say, well, we cannot vote for any block. And then they spread timeout messages. And we form what's called a timeout certificate that says, okay, it's okay to skip the round. This is what the ghost block here signifies. And you continue to the next round with a timeout certificate. However, not anyone can receive a quorum certificate, even if it's formed. So you might have situations where there's both a ghost block and a timeout certificate. So what is really needed for consistency is simply to wait for 2 consecutive quorum certificates before you can commit, not the entire chain, but the head of it. A timeout certificate may form when some participants didn't receive the quorum certificate, but if there's a chain of 2 of them, then the head of it cannot actually get a timeout certificate, only the tail. And so anytime you see a contiguous chain of 2 QCs, you can finalize not just the block, but the entire prefix. Now, for technical reasons that are beyond the scope of this presentation, in order to actually operate at network speed, we need 3 rounds, not 2. But the most important thing is that I've already told you in 2 minutes, essentially the entire algorithm. The only thing that validators need to remember are 2 numbers. The last round they voted on, they're only allowed to vote once in every round, and the highest round in which they saw a QC, and they're not allowed to vote on a conflicting proposal if the QC is from a lower round. So takeaways, Hot Stuff has become popular really only very partly because of its linearity. What really drove its adoption is that the simplicity and the developer-friendly manner in which it was written and presented, and the similarity that it bears, and what we borrowed from the tremendous, incredible innovation that was happening outside academia. To our knowledge, Hot Stuff now drives the core of many blockchains, including DM, as well as Flow, or Dapper Labs, Celos, Ethereum, and potentially others. And I think the simplicity is the one that really drives confidence in the resilience of these implementations. So I'm going to wrap up and say that I hope these stories were interesting for you, no matter what field you're in, and I'm happy to take any questions. Thank you.
Oh, thank you, Dahlia. Great talk. If you have any question, please send your question to the chat. So then I will follow your question. Anyone in the Zoom have questions? Okay, so let me take advantage of chairing the session. I have a question. I'm very glad to see the keynotes yesterday and today all touch the core issues of distributed systems, and in both foundational and system aspects. So my question is the comparisons between the Raft and Paxos. From my study on the difference between the system on the technical detail, the leader election is different, and in the slightly different ways. So in the Raft only allow the servers with the updated logs. So the Raft really follow the logs if you're updated or not. If you're updated, you can be candidates to become leaders. But for Paxos, it is allow anyone, and then also if you are updated. And this may make some difference. So what's your view about this difference, and particularly in productions? What make a difference in productions?
Yeah, Paxos gave the most minimal, Occam algorithmic framework in which you can plug in details of implementation as well as variants. So there's no comparison. Raft is a protocol in the Paxos family. I think that the main value in Raft is actually in passing contiguous prefaces. But as I said, the Raft was not the first one to observe this advantage. The way you pick a leader is important when you build systems to practice, but I don't think there's a wrong way. There's almost no wrong way to get it. I've never seen this become a problem. In Hotza, for example, we simply rotate the leader and remove leaders that have not participated in previous rounds so that we don't have to time out on faulty leaders. So there's some very crude reputation-based mechanism. The other reason, I think the other reason Raft is extremely impactful is because they took the effort to actually build an engineering grade solution and evangelize it and continue maintaining the project live, and not just hand out a white paper with the ideas. And that's tremendously valuable and tremendously important. At the same time, I do want to highlight and underscore that Raft does leave room for improvement. In Raft and in some prevailing implementation like XCD, you cannot manage arbitrary configuration changes, and you cannot manage well cascading configuration changes. What engineers tell me is that with Raft-based systems, you can remove or add servers to a cluster one at a time and have to wait until it quiesces before introducing another change, and some limitations that better algorithmic foundations could handle. The second thing I do want to highlight is that a lot of advances have been done between Paxos that Raft could have taken advantage of. Yep. Paxos is really the core minimal Occam framework, but there's a lot of other research as well.
Good, thank you. By the way, your intern Heidi Howard recently wrote a paper to compare the two protocols. I assume
Yes.
you read that paper. Okay, thank you. There are other questions from Louis Teng. Thank you for the great talk. I also see simplicity and developer-friendly design are very important for real system development. However, in my experience, most Tier 1 conferences do not share this view. Do you have any suggestion to address this issue, especially for young faculty who does not have deep relation and collaboration with industry? That's, I think, very suitable question to both academia and industry with experience like you.
I share the frustration. I would even expand it, and I did listen to John's keynote yesterday. Look, no system is perfect that I know of. I could extend the frustration. Not only is it easier typically to publish incremental results in a well-understood problem that has a line of advances, and it's very clear how you advance them, than to publish impactful results. Even if you address systems conferences, a lot of times you're expected, to produce unnecessary micro benchmarks or show at least 3 different implementations where where you're working on production system. This is kind of ridiculous. That said, it's the best system we have. I don't know of any other merit-based, relatively neutral, relatively objective system out there. If we throw it completely, we would probably penalize the entire scientific method that stood for hundreds of years with peer reviews judgment and publications. So my wisdom, my advice is to younger, researchers starting their careers or wherever you are, is try to focus on real problems. Don't optimize for quantity, but for quality. And don't be despaired by rejections. Everybody gets them. This process as a whole might look random or arbitrary. It's not. In the long run, if you consistently do good work, you will get rewarded for it. But don't look for that reward to be completely deterministic at every point of the way.
Good. Thank you. There's another question. Very interesting talk. Does hot stuff work in permissionless setting?
Thank you for the question. First, I want to say that Ted, the summer intern who worked with me on hot stuff, is about to defend his thesis in literally 2 hours at Cornell University. So this is a great day to talk about this. No, hot stuff was designed for a traditional setting where the number of participants is known, and the key concept by which blocks are chained to each other, the quorum certificate, is taking a quorum, in this case a Byzantine quorum, out of that known set. That said, it's very easy to reconfigure hot stuff. Every block essentially could determine a configuration for the next block. And this is in fact what we're doing in BFT. It's completely agile. And there have been some publications that try to adapt and take some properties of hot stuff into different settings. It will not be hot stuff, it will be something else, but there are many ways to combine.
Okay, thank you. Another question from from Edward. Based on your experience with the vertical Paxos, developers never use standard Paxos because it was too difficult to deal with holes in the log. Would you agree with John Osterholt that usability should be a metric for evaluating system?
Yes and no. Look, impact is important. The devil is in the details. How do you prove impact? How do you prevent it from becoming politicized? How do you prevent crowdsourcing that show, how many people downloaded my GitHub repo? Like I said, at the end of the day, I could say about the scientific world, the same thing I can say about democracy. It is not perfect. It is the best system we have right now. Be careful, when overturning it. I know that Google, Facebook, some other Silicon Valley companies tried to do research differently. They tried to embed researchers inside production systems and say, researchers should code and should be measured based on lines of code and contribution, the same as engineers. They've since then backed out of that, and they both have very credible, very impressive research organizations. So there's a reason why the scientific world works that way, and why experts in the field are the ones judging and reviewing papers and systems. And while I would like to see more impactful research being published in academic venues, we need to be very judicial about how to affect that.
Okay, thank you. I don't see any new questions. Delma, Abhishek, Sungqing, any? Oh, there's another one, sorry. Is Core4db developed as a production in Facebook?
No, so a new system called Delos, which is a rebuild of Kofu using Zookeeper as individual stripes or logs, and is written from scratch, has been developed at Facebook. It's built on the same principles, also obviously introduces some exciting innovation, and it's mostly used for elasticity, cluster elasticity management. So it's used for slightly different use cases than Kofu. Kofu, however, is still being maintained by VMware as an open source project. You can find it on GitHub.
Okay, thank you. Any other comments, questions here?
Just curious, what's the goal of the DM? You're working on this, you're trying to build a foundation for blockchain technology and offer services to other companies, or what's the goal?
So DM is a blockchain-based payment system that brings the opportunity to build a transparent, immediate finality, interoperable, and inclusive platform into a regulated arena. What we would like is to be able to program money, in the same way that you can program everything, but do it in a way that protects consumers, provides fraud management, prevents money laundering and any other kind of illicit activity, the way tens of years in the payment world, in the financial world, have evolved and matured into.
I see. So can I assume there's some sort of like centralized control, or because traditionally, like if we want to have better production on the user side, then we got to have some we have some concerns on anonymity and privacy and also security. Are there like a centralized control in the system, or that's still like distributed?
So the core platform, I can talk about DM forever. Let me just very, very quickly take this opportunity. The core blockchain is a permissioned blockchain. It is being operated by a consortium of members. We have 26 member companies as part of the DM association, who came together with the understanding that no single private sector company should gain the trust of an inclusive payment platform. This is the core platform deployment and operation. Now, to interact directly with the DM blockchain, you need to be a permitted, regulated organization at this point. And so privacy by design is for the users. The end users are users of the virtual asset service providers, or VASPs, that are permitted to interact directly to the platform. We do not collect or store or know any information about the end users. So you can think of it as a two-tier system where the users are serviced by omnibus accounts that VASPs manage on their behalf.
I see. Thank you. Yeah, are we going to see that? Is it already been deployed, or it's we're going to see that soon?
So we have a testnet deployed, and the code is open on GitHub for community scrutiny. We are and have been working with regulators to obtain all the permissions and all the oversight that is needed to launch the platform in the most secure and the most trustworthy way we can.
I see. Thank you. Looking forward to that.
There is another question. I think this should be the last question in the chat. What is the link to Facebook Telos?
Delos.
Delos. He said of Delos.
DLOS. I can post it later if you tell me where to post it, but it shouldn't be that difficult to Google DELOS, Mahesh Balakrishnan. It was also published in the recent OSDI conference and won Best Paper Award.
Okay. So Hashem, I think you can search Delos, DELOS. Okay. Thank you and congratulations again, Dalia. Any other
Thanks
comments?
again. It was a pleasure and an honor speaking to you today.
Yeah. Okay.
Thank you, everyone, for attending, and we look forward to see you tomorrow.
Yeah. Okay. See you tomorrow. Thank you, Dalia. Okay. Bye-bye.